Okay, this is the first introduction video for our new school year. And we're going to start off in Chapter 6, Section 6.1. We just finished up Chapter 5 last semester. And now we're actually going to apply what we've learned. So we're going to apply integration. In Section 6.1, we start off and we're talking about velocity, net change, and future value, which are really important on the AP test. They will give you a contextual problem. And this will be the key to getting a lot of points on the AP test. And what we start with the fundamental theorem of calculus. If you remember the fundamental theorem of calculus, this is the first one, not the second. And the fundamental theorem of calculus, the first one, if we integrated from some a value to some b value of the derivative of a function, so we'll call our function f, and our derivative is f prime of x, dt, that gives us f of b minus f of a, where f of b is some future value, and f of a is a given value. Sometimes that given value is the initial value, sometimes it's another one. So that's where those initial value problems come from, and they're boundary value problems. That's what they're called in calculus. And f of b minus f of a is the net change in f, which that becomes really important. We are looking for net change. All right, so if you're doing a future value problem, then you would solve for the future value. And that would equal f of b. And to solve for f of b up above, you would just add f of a to both sides. So you get f of a, which is the initial value or the whatever given value, some value they give you. And then you're adding the net change, how that function is changing over that time period. And this is particularly good when they give you a value and they want you to find something at the future value, but it's also good generically for any problem where it's an accumulation problem. So basically the generic way to do this is we call it some quantity q. Some function, there's a function of this, how this quantity is changing. We're accumulating something or losing something. And we'll call it q of t. And if we're given some initial value for it, if we add the net change, how much it has changed over that time period, we'll have the future value. But this is more generic. This is particularly for initial value problems. If we start at 0 and we integrate to some future time t, and we integrate the rate of change of q, which is the derivative of q, and for these problems, t is greater than or equal to 0, so we're starting with an initial value. And then what's going on is we're taking that initial value they gave us, and we're adding this net change in Q. Now notice I left the T in there. If they give you a specific value they want you to go to, you would put it in. But in this case, this is like solving those problems where you were given a derivative, a differential equation, and you were told to find the family of curves or the family of solutions, and you did the antiderivative. You had a plus c, you plugged in the initial value, so you got the family, and then they wanted a particular solution, so you plugged in whatever they gave you with the initial value or the value somewhere else, and you found c. Well, what this does, this formula lets you do that without actually going and get c. So this works for the indefinite and definite integrals when you do this like t. And in this case, remember, the derivative is the rate of change of q. So when you integrate it, you get how much q has changed, which is the net change. That's how much you've accumulated or lost. All right, what is this used for? Let's start with the velocity. There are other problems, and we'll get to those. But there's velocity problems. And in particular, what they're looking for is displacement and total distance. And you've done total distance, but you did it for derivatives. And anytime the particle changed directions, you had to find the changes in directions by setting the velocity equal to 0. Remember that? And then everything that was a negative length, you made positive. Well, it's much easier with integration. We can do this a lot easier. We still need to know that when it changes, but we'll get to that. So first off, let's review it real quick. We have position. And we'll just use the s of t, because that could be x or y direction. We only do one-dimensional right now. We'll do two-dimensional later. Then we do velocity, which is v of t, and that equals to the first derivative of position. And then there's acceleration. That's a of t, which is equal to the first derivative of velocity, which is the second derivative of position. So for displacement, you've actually been finding displacement. You may not have realized it. We were just learning to do antiderivatives. And then we did definite integrals. Well, those definite integrals you were doing, if we said one of those functions you were integrating described how some quantity was changing, when you integrated it, you were finding displacement. So displacement, remember displacement for physics is the final position minus the initial position. Well, how do we find that? Well, we integrate velocity, because velocity is the first derivative, or it is the rate of change of position. So if we integrate it, we find the net change in position. That net change is is displacement. To find total distance, we just need to make all of the, because remember, these are areas. Those areas are like when I drew remember the 60 miles an hour? Where the area underneath the rectangle was the total miles accumulated. Well, total distance is the integral, so that means it's the areas. And what we're doing with total displacement, we're saying we're going to add up all the positives and we're going to subtract all the ones below the x-axis, which are negative, to get a total distance, total displacement. To get total distance, we take all those negative areas and flip them up. Well, the way we do that mathematically is do absolute value. And we'll get into this more. But basically, we're taking all the negative areas, ones underneath the curve, flipping them up, and that's the total distance. And future positions, is equal to some s of t, and that's the initial position plus the integral from 0 to t of some velocity. Notice the difference in variables, because we're going to plug the t in. It has to be in terms of x's. And then there's a future velocity, so that's v of t. The equation describing the velocity is the initial velocity plus the net change in velocity, which the change in velocity is described by the rate of change of velocity, which is acceleration. So we're going to get from 0 to t of the acceleration with respect to x, dx. And all you do is just change the variable to x. And that's all I want in the intro video. In class, we'll start doing some examples.